Let me share my screen. Okay, so I think this is where we ended last meeting. We ended with the self-test, which has 2 items regarding the manner in which we determine the rate expression based on the stoichiometric equation provided in the case of the first number, and then on the second number, actually we just need to substitute values, concentration values, to the equations that we have set up in the first. So for today, we're going to discuss kinetic models for non-elementary reactions. So non-elementary reactions actually are most of the time overall reactions after we have already simplified the series of reactions that brings about the final product or products from the initial reacting species. Now, there are very important key assumptions which we will use in proving the correlation. So it need not be at all times that they are correlated, but if the problem is already implying that there is correlation between the provided rate equation and the mechanisms, then all you have to do is prove the correlation using these key assumptions. So what are these key assumptions? So number one assumption, you are provided in the sense of your reaction mechanism, you are provided with a sequence of, so take note of this assumption, elementary reactions in which the amount of intermediates formed are non-measurable or non-observable because their amounts are negligible. Thus, what are observed are the initial reactants and final products only, which most of the time appears to be just a single reaction. And this particular single reaction is actually the overall reaction. So this first assumption is that you are given elementary reaction. So since you'll be given a mechanism, so it will comprise of a series of reactions. You are to view this series of reactions all as elementary reactions. The second assumption is also part of this statement in that the amount of the intermediates are negligible or non-measurable. So negligible or non-measurable because their amounts are very, very small. It's not that there's no amount formed for this intermediate. It's just that upon their formation, right away, they are being consumed in the next steps. So if you, at any particular time, if you're going to look at it, the amount that remains is very negligible. So that is why the amount of intermediates that are formed are non-measurable or negligible. So we're going to use these two major assumptions in our reaction mechanism. That way we can prove the relationship or the correlation between the rate equation that is provided and the reaction mechanism. So for example, I'll give you this was already shared to you last meeting. This is an example. You're given this hypothetical reaction in which A sub 2 and P sub 2 is reacting to form 2 moles of AB. Okay, now this is the main reaction, or shall I say the overall reaction that is provided. Together with this overall reaction, you are given this reaction mechanism, and that is A sub 2 reacts, or rather decomposes, to form 2A asterisk. Okay, 2A asterisk in this reversible reaction, and that in this particular formation of 2A asterisk, A asterisk forms with another or reacts with another species, which is B sub 2, to form AB, the product AB here, and another intermediate, which is B asterisk. So the components, by the way, which has the asterisk, are what we call as intermediates. Now, the third step is the reaction between intermediate A asterisk and the second intermediate B asterisk to form more product AB, or the final product AB. Now, this is the mechanism that brings about this overall reaction. So using what you have learned in Chem 1 then, how to get the overall reaction, all you have to do is add all these reactions in your mechanism of reaction. So what you do, you have A asterisk here and A asterisk here, so that would be 2A asterisk. It then will cancel with this 2A asterisk on the other side. And then you have this B asterisk also canceling out with this B asterisk on the other side. So what is left is actually the A sub 2 plus the B sub 2 that you have here, forming 2 moles of AB. So our mechanism of reaction, or our series of reaction, actually brings about that single reaction, which is oftentimes the overall reaction, after we have added all the reactions that were provided or that is present in the mechanism. So this is an example of such. So this is your overall reaction, and this is what the problem gives you. And the mechanism for this overall reaction is the one that is written here below. So later, after I have discussed already the types of reaction intermediates, we'll go to the actual proving process of making a connection between the provided mechanism and the rate expression, or the implied, as suggested or explained in the problem, rate of reaction. Okay, so but before we go to that, since we're talking about intermediates here, let's discuss what are these reaction intermediates as covered and discussed in Levenspiel, active Levenspiel's chemical reaction engineering. So we have here the types of reaction intermediates. So you could see them with the asterisk, you could see them with the minus or plus sign. You will learn as we go along, okay? So the first part or the first type of reaction intermediates are what we call the free radicals. So these are free atoms or larger fragments of stable molecules that contain one or more unpaired electron or electrons. So they are generally very unstable and highly reactive, and as such they are intermediate because considered as intermediates because once they are formed, they react right away. So at any particular time, their amount present is negligible. Now, these are free radicals, which is designated by a dot on its chemical symbol. So aside from seeing asterisk on intermediates, it's also possible that you'll be seeing dots after the symbol of a particular compound or molecule. And as such, this one are to be viewed as free radicals or reaction intermediates. So they are generally unstable and highly reactive. Now, the second type of reaction intermediates are the ions and the polar substances. So since they are ions, they are electrically charged atoms, molecules or fragments of molecules that acts as active intermediates. So they are electrically charged primarily because some are ions, considered as ions. Now, I mentioned a while ago that aside from seeing asterisk, you may either see a negative or a positive sign on the formula of the molecule or the compound. So these are examples of such. So these are ions and polar substances. So considered as well as reaction intermediates. Now, the third types are the molecules. In the case of this two-step series reaction in the formation of the final product S. So this R is a intermediate. It's a molecule. It's in the form of a molecule. Now, we also have transition complexes for this intermediates, and these are strained bonds or unstable forms of molecules or unstable association of molecules which resulted from numerous collisions between reactant molecules. So transition in the sense that they are just transitioning from one form to another. So after they are formed, they decompose further or react further to form another substance in the mechanism. So that is why they are termed as transition complexes. So we have four different reaction intermediates here. We have the free radicals, we have the ions, and the polar substances. You can also have the molecules or the transition complexes. Now let's go to the schemes of the reaction mechanism. So there are actually two schemes in which your final product is being formed from the intermediates, which were also formed initially from the reacting species. So let's look into these reaction schemes. So we have the non-chain reaction. So these non-chain reactions, for these non-chain reactions, the intermediate is formed in the first reaction and disappears as it reacts further to give the products. So a classic example, hypothetical representation is that initially you have the reactants, it forms this intermediate or intermediates, then these intermediates form further or react further rather to form the products. So this is a non-chain reaction because after the first reaction, the intermediates that were formed are reacting further right away to produce the products or the final products. Now we have the non-chain type. The chain type are the one that you could see in here. So the intermediate here is formed in the first reaction, which we call as the chain initiation step. Since it's the first, so it's the initiation step. So since it's a chain, so chain initiation step. Now this combines to form the product and more intermediates. So it was already formed in the first reaction, but it reacts further in the second to form the product and more intermediate in the second. And in this particular second step, we call it the chain propagation step. Propagation in the sense that the intermediates are being propagated. So they don't just form the final product or products, but more intermediates are being formed in this particular step. So chain propagation step. The last is the chain termination step. Termination in the sense that we're referring to the intermediates again. So they are being destroyed in this last step, or their presence is terminated in the mechanism of reaction. So the initiation step, the propagation step, and the termination step. Excuse me, class. Okay, so that's it, class. We have the non-chain and the chain reaction. Now, there's a note in here that in the propagation step, the intermediate is not consumed yet, but acts as a catalyst for the conversion of the material. So it's being propagated, but at the same time, it acts as a catalyst for the conversion of the material to the final product. So our mechanism of reaction can either be the simple, the non-chain, or the chain reaction, but oftentimes, class, it's in the form of the chain reactions. Now, having learned this already, preparatory to the proving part, we go now to the sample problem wherein we can use the assumptions that were discussed at the start of the class. So this is our sample problem. Let me just enlarge this one. So show that the given reaction scheme or this reaction mechanism proposed by Og is consistent with and can explain the first order decomposition of dinitrogen pentoxide. So there was no provided rate equation here, but it's simply saying that you are to prove that this mechanism is consistent with the observed first order decomposition of dinitrogen pentoxide. So for us to be able to do that, And so that we won't have to go back to this particular slide here, allow me to go to the Jamboard and then have this particular given information. I'll just copy it. Okay. Let me first go to the board. Okay, let me share new screen. Okay, here we are. So I'd like to rewrite our given information here, our reaction, the provided reaction mechanism. So we have the reversible reaction in the conversion of dinitrogen pentoxide into nitrogen dioxide and nitrogen dioxide. So this is your intermediate here. And we have this rate constant, K sub 1 for the forward reaction, and we have K sub 2 for the reverse reaction. Then for the second, we'll have NO3, the intermediate that was formed in the first, now forming another intermediate, nitrogen oxide and oxygen. So we'll have the rate constant here, K sub 3. The last is the reaction intermediate, nitrogen oxide reacting with another intermediate, nitrogen dioxide, to form, so this is our rate constant, to form 2 moles of the final product, dinitrogen dioxide. Okay, so this is the reaction mechanism that is provided by the problem, and we are to prove that this is consistent with the first order decomposition of dinitrogen tetroxide. So coming from that particular phrase that it is a first order decomposition of nitrogen or dinitrogen pentoxide, then the rate of the reaction based on the nitrogen pentoxide should be equal to K times the concentration of dinitrogen pentoxide. Or it could be simply written as K based on dinitrogen pentoxide times the concentration of dinitrogen pentoxide. So it's first order kinetic, so it follows that the concentration based on dinitrogen pentoxide should be raised to 1 because it's first order. So this is how we translate that particular phrase, which says that it is consistent with the first order decomposition of dinitrogen pentoxide. So we will prove the correlation of this rate law to this particular reaction mechanism. So the first thing that we are to do in here, whenever you're given a mechanism that has a reversible reaction, is you're going to write this particular reversible reaction into 2 reactions, equivalent reactions. So this is what I mean. You write here dinitrogen pentoxide. That's for the forward reaction, forming NO2 and NO3 asterisk. Okay? And then what you're going to do, you're going to write again the reverse reaction. So this time your reacting species will be your nitrogen trioxide and your nitrogen dioxide forming the dinitrogen pentoxide. Okay, so that's it. You have to rewrite this reversible reaction into its equivalent reactions, into these 2. The others, there's no need to rewrite because they are anyway single reactions only. Then after that, you have to look for the reaction that has the presence of dinitrogen pentoxide. So if you're going to look for that reaction or for those reactions that has the presence of dinitrogen pentoxide, Allow me to use a different color here. Those reactions would be this, this. That's it. Because the last two reactions here does not have the presence of dinitrogen pentoxide. This is where we're going to start in terms of writing the net rate of reaction of dinitrogen pentoxide in your reaction mechanism. So what do I mean with the net rate of reaction of dinitrogen pentoxide? So allow me to go to the next part. We're going to write the rate of reaction of dinitrogen pentaoxide is equal to, I have written it here as negative, so meaning when I write this net rate equation, I'm looking at dinitrogen pentaoxide as a reacting species. So in this particular reaction here, your dinitrogen pentaoxide is a reacting species, so we don't have any problem. I will use this rate constant K sub 1 together with the concentration of dinitrogen pentaoxide. So we'll do that. So I'll write here K sub 1 C of dinitrogen pentoxide. That's for the first reaction that we have here. However, your dinitrogen pentaoxide in the reverse reaction is being formed. And since I already started writing it here as species, then when I write here the term that will account for the formation of dinitrogen pentaoxide in the reverse reaction, it would be then negative. Negative in the sense that dinitrogen pentaoxide is not actually being consumed in the reverse reaction but being formed. So I place here negative. If just the case, if there's a case where in class this is not a reversible reaction and you have two reactions wherein your dinitrogen pentaoxide is all or is part of the reacting species, then instead of writing this as negative, because you have written already negative here, it should be plus. It's only negative in here because it's considered to be a product in this case in the reversible reaction. So in the reversible reaction, it's not anymore a reacting species. So what's going to appear in your rate law, because we're going to look at each of these reactions as elementary, will be the reacting species here. So what I'm going to write now is K sub 2 concentration of NO3 asterisk. You see it here, and then concentration of NO2. So the manner in which I write the rate law for my reactions that are present, which has the presence of dinitrogen pentaoxide, is based on the concentrations of the reacting species and based on their coefficients. In this particular case class, their coefficients are just 1, so I need not write any exponent other than 1 in here. So this is our main, shall I say, net rate equation, which we're going to translate or convert. We're going to convert this net rate equation into this equation here, which says that it has a first order decomposition with respect to dinitrogen pentaoxide. Okay, so this would be our first equation. Now, the next thing that you do after you have written the net rate equation based on the species that is appearing in the rate law that you need to prove correlation with your mechanism is that you set up equations that will, shall I say, be replaced in here, or that would be a source of an equivalent expression for the concentration of the intermediate that appears here in our first equation. So I need to set up an equation based on NO3, or that's nitrogen trioxide. Where am I going to get it? Of course, I go back to my reaction mechanism and I'm going to set that up as well. So I will write here the rate of consumption of nitrogen dioxide. So I'll place here, it's an intermediate. Okay, and I will write. Now, here in the first is a product or one of the products of the first reaction. Your reacting species is dinitrogen pentoxide. So just like what I did here, since I place in here negative, then I'll place here negative. Case of 1, concentration of dinitrogen pentoxide. So we always write the rate law in terms of the concentration of the reacting species. But we have to account for the presence of NO3 here. Okay? Now, in the second, your NO3, your nitrogen trioxide, is already a reacting species. And by the way, this is case of 2. Okay, I'm just writing the rate constant. So we will write the corresponding rate law for this. NO3 and NO2 in this case. Species, NO3 is reacting. So I'll place here plus K2C NO3 asterisk CNO2. Okay? That will account for the presence of NO3 here. Now, in the next reaction, we have another NO3. So this time you need to add another rate expression for that. Then it's a reacting species here. So you'll have K3 CNO3. Okay? For the third reaction. For the last, you still have NO3, so you need to account for it as well. It's together with NO. So you will have K sub 4, CNO, and CNO3 asterisk. So in this net rate of reaction of nitrogen trioxide, you have 4 terms. Primarily because in all of our reactions, NO3 is present. Okay, you have NO3 here as product, you have NO3 here as reactant, the same thing with the third and the fourth reaction. Okay, now after you have set up the net rate equation based on this intermediate, you will set the rate of reaction equal to 0. We set the net rate of reaction equal to 0 because at any particular time, there's going to be no change in the amount of this intermediate because as based on the assumption, the amount is negligible. In a sense, in that particular premise, then we say that the rate of reaction is 0 or more or less 0 because there's no change in the amount of such an intermediate. So we set this particular equation to 0. And what we do, we factor out the terms that has the, before we factor out, we set aside the terms here that contains the concentration of the intermediate nitrogen trioxide. What's the purpose of having to set aside the terms that has the concentration of the intermediate NO3? We want to set up an equation which will replace this one, the concentration of NO3 in our equation 1. So that's the main purpose. So I will have here K sub 1 concentration of dinitrogen pentoxide plus I have here CNO3, CNO3, CNO3. To save us some lines in our solution, I will factor it already. So concentration of nitrogen trioxide, and I will have it multiplied to K sub 2 CNO2 plus K sub 3 plus K sub 4 CNO asterisk. Okay? Now I can transfer this on the other side to make it positive. So I will have K sub 1 concentration of dinitrogen pentoxide, and I will have here concentration of NO3 asterisk, and you'll have K2 again, CNO2 plus K3 plus K4 concentration of nitrogen oxide. Right? Now, as I said a while ago, our goal is we will replace the concentration here of the intermediate in our main net rate equation based on the species that appears in the rate law that we need to correlate with our reaction mechanism. So we will have now equation 2, which will give us an equation to replace the concentration of intermediate NO3 or nitrogen trioxide in our first reaction. So this would be in this form. The numerator is K sub 1 concentration of dinitrogen pentoxide, and your denominator would be K sub 2 C NO2 plus K3 plus K4 C NO asterisk. So this now is our equation 2. Okay, so this is now our equation 2. Now, before we even think of substituting this concentration of NO3 asterisk in equation 1, you will notice that there's another concentration term here, which is that of another intermediate, which is nitrogen oxide. So before you even substitute it here, make sure that you will replace this first with another expression. That way, when you substitute already the concentration of nitrogen trioxide in here, it does not have any more concentration of reaction intermediates. So I will set up another equation for the net rate of reaction of nitrogen oxide. So I will write here net rate of reaction of another reaction intermediate, which is nitrogen oxide. So we will go back to our mechanism and check in which particular reaction does nitrogen oxide appear. So it doesn't appear here, doesn't appear here. It appears in the third and in the fourth reaction. So in here, it appears as a product. So what I'll do, I will write negative for the starting term because I considered nitrogen oxide as a reacting species. So K3 and NO3, but that would be negative. So I'll place here negative K3 concentration of NO3 asterisk. Okay? And then we have another one here where it's already a reacting species, NO and NO3, with K4 as the rate constant. So it's reactant, so plus K4 concentration of NO3 asterisk concentration of NO asterisk. Let me check. So it's NO3 and NO and K4 as the rate constant. So it's in here. Now what I'll do, I'll set this again to 0. And I will have negative K3, the concentration of NO3 asterisk, plus K4, concentration of NO3 asterisk, concentration of NO asterisk. Okay, you could see from here that you have concentration of NO3 in both terms, and this being equated to 0, you can have it cancelled by division. So from here, we will have a simplified equation. If I transfer K3 on the left side, I will have K3, now positive K4 concentration of nitrogen oxide, an intermediate. So I can get now an expression that I can replace the concentration of NO in our equation 2. So that would be K3 over K4. So this is our equation 3. Now what I'll do, I'll substitute this equation 3 in here, in equation 2. Okay, so we'll go to the next slide. So you have substitute 3 to equation 2. So our equation 2 gives us the concentration of NO3 asterisk. And let's see what we have in the numerator. So K1 CN2O5, and our denominator is K2 CNO2 plus K3, and then K4 CNO plus K4, and NO will be this K3 over K4. So from here, you can see that we can cancel the K4s. Now this can be simplified into the form. You have K1, C, and 2O5. You have K2, C, and O2 plus 2, K3. Okay, 2, K3. Now this will be our equation 4. This equation 4 should be substituted now to equation 1 because it doesn't contain any concentration of the any intermediate. So it will replace the CnO3 in our main equation. So going back to our first equation, K1, concentration of dinitrogen pentoxide. So we have the rate of reaction based on dinitrogen pentoxide is equal to K1, C, and 2O5. And then we have the second term, which is K2, CnO3, CnO2. Minus K2, CnO2. The CnO3 I will replace by the equation 4 that we have made. So minus K2 CnO2, this one, I will replace by our equation 4. Okay, so I will multiply this by K1 CN2O5. Oh, sorry. Set O5. Then we have K2 CnO2 plus 2 K3. Okay, you have something like that. We can simplify this. If you notice, we have K1 C concentration of N2O5 in both terms. So I can have it factored out. So the rate in terms of dinitrogen pentoxide is equal to K1 C and 2O5. It will be multiplied to, we have 1 for the first term, if we factor out this one. And in here, in the second one, we have K2 CnO2 so minus okay, that's our numerator CnO2, and then our denominator will be K2 CnO2 plus 2 K3. Okay, K2 CnO2 plus 2 K3. So that's our denominator now. Now, if you look at this particular rate expression or rate law, because it does not have any derivative, doesn't yet look like similar to the first one that we have written. It will represent a first order decomposition of dinitrogen pentoxide. So this is the part wherein you make plausible assumptions. Plausible meaning acceptable assumptions based on the mechanism of reaction. The meaning your assumption should be based on the mechanism of reaction, this one. That way, from this rather complicated expression that we have here, the final equation that we have here, we can convert it into something like this only without this. Now, in making plausible assumptions, you are to use the reaction mechanism that is provided. So this is where you're going to base your assumption on. Now, if I'm going to ask you, before we make those assumptions based on our reaction mechanism, the only way that we can make this final equation on the right side equal to a simple K1C sub N2O5 is that this one, this would be equal to, this should be equal to what?
1, miss.
This one?
0,
Zero
miss.
rather, miss.
0.
Sabi
Because
ko
if
bilog na
this,
bracket, miss.
okay. If this is 0, then you are multiplying only the first term by 1. So then the the scheme that is given by OG is acceptable. So it's really that of a first order decomposition of dinitrogen pentoxide. So what do you think is a plausible assumption, acceptable assumption that we can make out of our reaction mechanism? That way we'll go back to the main rate law, which gives us the first order decomposition of dinitrogen pentoxide. What do you think would that be? So we have this.
K2 equals 0, miss.
K2 is equal to 0. Okay, let me check. If your K2 is equal to 0, so this will be 0. This will be 0. So 0 over divided by something is 0. Or is there a better way of phrasing that, Drexel? Aside from saying that K2 is really equal to 0. Because if K2 is equal to 0, why write it then as a reversible reaction? If it's 0, then Og would have simply written it as a single reaction, a simple irreversible reaction without this reverse path. So how do you polish that particular assumption? That way we don't say it's really 0. Because if it's 0, then there's no point of Og writing this reversible reaction here. He could have written only an irreversible reaction in the first place. How do we polish that particular assumption?
Assuming K2 is negligible, miss.
Assuming K2 is negligible, or what's a better way of saying it? K2 is negligible, or another way of stating it is, or what? Very small compared to what? Where are we going to compare it?
Compared to K3, miss.
Correct. Compared to K3. This is the assumption that you will make. It's either you say K2 is negligible, you cannot say K2 is 0 because that will make the mechanism wrong already. So it's either you say K2 is negligible, meaning its value is very small compared to K3. If you look at it, if this one is very small, and you divide it with something that is very big compared to it, a very small quantity divided by a very big quantity will result to a very, very small quantity because it's already small. If you divide it further by something that is very big, it's very small. This very small quantity, if subtracted from 1, will simply make it like subtracting nothing from 1. So this would be 1. So therefore, then, the mechanism that is provided by OG is okay in terms of it representing the first order decomposition of dinitrogen pentoxide. We say here where the K1 is the rate constant of the forward first step reaction of the forward. In this particular scheme that we have, what is this? What scheme is this? The original mechanism that is given to us by OG. What scheme is this?
Chain.
chain reaction. So this is the chain, what we call this particular step, the chain,
Initiation.
okay, chain initiation step. So the rate constant of the forward chain initiation step. If you have more than 3 steps in your mechanism, you cannot anymore use this terms chain initiation step, because in the case of the non-chain reaction, the general representation is just chain, propagation, and then termination step. So you can simply use in the first step or in the first reaction or something like that. So this is now your proving process. So this is how you prove the correlation, or you show the correlation between the provided reaction mechanism and the implied or stated rate law. So in this particular example, I have chosen this, that you are not provided with the rate law. That way you will be the one to write it, because it's not all the time that the proving part is already like finished in terms of you're given the mechanism and you're already given the rate expression. Sometimes you are even the ones who are writing the rate expression. You can see that, you can check that in the chapter and problems of octave Levenspiel in this part on kinetics of homogeneous reactions. Do you have any questions so far on the proving? So at times we're in the final rate expression that you have does not conform with the provided rate law, or does not conform with your own rate law based on how the problem describes it, then you just make assumptions. As long as those assumptions are acceptable, then you're okay in terms of the proving. It's not just that you just make any assumption. It has to be plausible. It has to be acceptable based on the mechanism that is provided. So any question here? If there's none, I will stop sharing. Okay. So since there are no more questions, I'll stop recording.